Okay, so welcome back, and let's move on. And I want to talk about what it means for two events to be mutually exclusive. So let's do one more quick example. Let's suppose that I do an easy experiment where I toss one die, a six-sided die, a single time, and I let A be the event that the number that comes up is even. So I won't show you the details, but you should know that that has a probability of 1/2, 3 out of 6. The even numbers are 2, 4, and 6 out of my 6 possibilities. And let's let B be the event that I toss the number 5. So what's the probability of throwing a 5? That's, of course, 1 in 6. And so let's suppose I ask you to find the probability of A or B in this experiment. And, well, you could do this using the addition rule that I just taught you, but let's just think about it again. What's the probability that I either toss an even number, that means I've tossed either 2, 4, or 6, or I toss a 5? Of course, of my 6 possibilities, there's 4 different ways that that can happen. So that probability is 4 out of 6. And notice that even though I said you can't just take probabilities and add them, but 3 out of 6 plus 1 out of 6 does equal 4 out of 6. So in this case, it did actually work out that I could just add these probabilities together to get the probability of A or B. And you say, well, what happened? You told me this PA plus P of B minus the probability of A and B is the way we calculate a probability like A or B. And the answer is that this is the same thing that we did here. And to show that, just think, well, what is the probability of A and B occurring in this case? If A is the event that I throw an even number, that means I throw either 2, 4, or 6. And B is the event that I throw the number 5. What's the probability that both A and B happen? What's the likelihood of me throwing both an even number and a 5? Well, that's actually 0, because there is no number that is both even and the number 5. So in this case, I still did my addition rule. It just so happened that when I found the probability of A and B, it was equal to 0. The probability of A plus the probability of B minus A and B is still my 4 out of 6, or 2/3. So when this happens, when I have two events that cannot simultaneously happen, and what that means statistically is that the probability of A and B occurring is 0. If I have two events that cannot occur at the same time, I call them mutually exclusive. And an easy way to visualize this is that if I think about A as being sort of the set, A is one event, and I think about its set, its event space, a set of events of A, and B is another event, and it has its own space. Two events are mutually exclusive if there is no common element in both of these sets. When I wrote down my list for 2, 4, 6, that was my even numbers, and I wrote down 5. These are two sets that are completely disjoint. They don't have anything in common. There's nothing that goes between these two sets. And so if this occurs, these events are mutually exclusive. You can also visualize it with Venn diagrams. If I think about the probability space of A and B, if there's any overlap, that means that there's some possibility that something can happen where both A and B have happened. Then these events are not disjoint and they are not mutually exclusive. But if it's the case where A and B have no chance of both happening in a trial of my probability experiment, then they are mutually exclusive. These are mutually exclusive events here. So as an easy example, we can think about the experiment where I just pull one card from a randomly shuffled deck, and let's let A be the event that I pull a king when I pull this card out, and let's let B be the event that I pull a heart. So are these mutually exclusive events? Well, all you need to ask yourself is it possible for me to both pull a heart and pull a king? What's the probability of A and B occurring? And is it equal to 0? Well, you can look at the diagram down here. I can represent my one event space. The probability that I pull a king is actually 4 out of 52 because there's 4 kings in my deck of 52. And I can represent it with this space here. The probability that I pull a heart is 1 out of 4 or 13 out of 52 because these are my 13 hearts. And look, it is possible for me to pull both a heart and a king. All I have to do is pull the king of hearts. That's a card, and it's possible I pull that. So these are not mutually exclusive events. The probability of A and B occurring is not 0. It is greater than 0. If you want to know what it is, it's actually 1 out of 52. 2. Doesn't matter how small it is. If it's not 0, it's not mutually exclusive. I'll denote that ME. On the other hand, if I stick with my original event for A and let that still be the event that I pull a king, and I call C the event that I pull an ace, these are mutually exclusive events because there's no way that I could pull a king and an ace from the deck if I only pull one card. The probability of me doing both of these things is 0. There's no single event, there's no single outcome in my entire sample space of all 52 cards where both A and C would happen. For that to happen, I'd have to pull an ace and a king with only one card. But since that's impossible, this probability is 0, and these events, yes, are mutually exclusive. Okay, so now I'm going to jump forward a second, and I'm going to talk about conditional probabilities in particular, and we'll get to another type of way we can classify events, and that's dependent or independent events. But first I want to take a quick reminder of the way we can multiply certain probabilities in statistics. So let's do a quiz just for fun, and I'm going to give you a 4-question quiz right now. I want you to answer these 4 questions just for fun, Who says math is not fun? My first question is true or false? 0.99999, where 9 is a repeating decimal, equals 1. Do you think this is true? I don't mean round off. I mean, do you think these are the same numbers on the left and right-hand side of this equal sign? Question 2, how many months have 30 days? 12 months, 4 months, 11 or 7. Question 3, true or false, you put toast in a toaster. And question 4, repeat the word silk 5 times quickly. Silk, 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 silk. And then quickly tell me what cows drink. Finish this quiz, write down your answers, and we'll take it up in 1 second. Okay, so what are the answers? Let's see. Question number 1, it's true. Did you say false? It is true. This and this are the same number. I have to explain that to my calculus students sometimes when I talk about limits and stuff. But these are actually the same number in mathematics. And if you're curious about that, you can ask me in class. Question 2, how many months have 30 days? 11 months have 30 days. Even those months with 31 days, they have 30 days in them, don't they? Is that tricky? Maybe, but this is just for fun. True or false, you put toast in the toaster? I hope not, because if you put your toast back in the toaster, it will burn. And the last question, what do cows drink? Cows drink water. They don't drink any of this stuff. So just for fun, how did you do? 2 out of 4, 3 out of 4? I don't know. 4 out of 4? Maybe you did. So let's suppose that you had no idea about any of these answers and that you closed your eyes and took a random guess at these questions. If a computer just picked randomly either true or false, and then picked randomly A, B, C, or D, and then picked true or false, and then picked A, B, C, or D, here's a question for you. What do you think the probability is that that computer would get every single question right? Think about it for a minute and try to come up with a number. And so what's the answer to our question? Well, if you got to write the answer, I'll tell you, I'll spoil the ending for you. The answer is 1 in 64. And how do we come at that number? Well, think about what happens at each sort of step of this quiz. At the first step, I have 2 choices of answers. I could pick either true or false. There's 2 possible outcomes in the sample space if my quiz was only one question long. And of course, the probability of guessing right is 1/2. If I add another question, we've already sort of seen this with probability trees, then if that second question has 4 possible answers, then for each choice I'm adding 4 new possible responses. So it stands to reason that my total number of possible responses for the 2-question quiz is 8. And notice that the probability of guessing the second question right is 1 out of 4. The probability of guessing the first question right is 1 out of 2. And the probability of closing my eyes and picking one of these answers and getting it right is 1 out of 8. In other words, these 2 probabilities multiply to give me the probability of getting both questions right. And so what this example illustrates is something called the fundamental counting principle. And all that says basically is that if one event can occur in m different ways, and the second event can occur in n different ways, then the number of ways that both of these events can occur, one after the other, or in sequence, is m times n. For example, if I'm waking up in the morning and I need to put on a pair of pants, a shirt, and a pair of shoes, and if there's 2 ways I can make my first choice, I can pick one of 2 pants, 3 ways I can make my second choice, and 2 ways I can make my third choice, then the total number of ways that I can get dressed. The total size of this sample space is going to be 2 times 3 times 2, which is 12 total outfits that I could wear. So what does that mean for our quiz? If I take the counting principle into account, there's 2 ways for me to answer a true or false question, 4 ways for me to answer my multiple choice question. So that means that there should have been 2 ways for me to answer the first question, 4 the second, 2 the third, and 4 the fourth. And when I multiply these together, it tells me how many ways I can answer the quiz. If you're a teacher and you give a quiz like this, there's 64 possible solutions to that quiz. Or it's 64 possible answers, only 1 correct solution. And so the probability of somebody closing their eyes and randomly answering all 4 questions right is actually only 1 in 64. So our point here is that in order to find this 1 in 64, I could write out the whole sample space of 64 outcomes, or I could just multiply the probabilities as I go. Because notice that 1 in 64 is the same as 1/2, which is my likelihood of guessing this first question right, times 1/4, which is my likelihood of guessing the second question right, times 1/2 times 1/4. And this also equals 1 over 64. So let me give you an example of how we might use the fundamental counting principle here. So let's suppose that you're on a jury or something like that, and you're presented with the following evidence. There's a man on trial for armed robbery, and the evidence against him is as follows. 2 witnesses who heard the man at the robbery were given a choice to listen to 5 different audio recordings, A, B, C, D, or E. And each of these witnesses, one of these people, let's say it was D, just for fun, happened to be the man who's on trial. And each of these witnesses, after they listened to these 5 audio recordings, those are supposed to be headphones, not a 1950s haircut, and each of these people correctly identified the man who is on trial. So the question you need to ask yourself is this evidence that they were actually hearing the voice and recognized it? Or is there a chance that both of them could have made the same selection by randomly picking? So your question is, in this scenario, if people closed their eyes and picked at random, what is the probability that they would both pick the accused in this scenario? Think about it for a minute. I'll tell you the answer in 1 second. Okay, so what's the answer here? Well, let's visualize this experiment first, of course. So what I have is 2 different selections occurring. I can think about sort of the first event in this little experiment being the first witness is picking who he heard on the tape, A, B, C, D, or E. He's picking one of 5 voices that he thinks represents the accused. And how many ways can that happen? There's 5 different ways, of course, A, B, C, D, or E. So if I compound this by adding my second witness selection, which is this second selection here, I won't go ahead and write it, then I get 5 additional ways for each of these ways. So that makes 25 total ways that these 2 witnesses could have picked somebody. And that's represented over here. This is the sample space. They could both pick A, they could pick A and then B, they could pick A and then C, and so on and so on. So I have a sample space of size 25. If only one of these people represents the accused, then there's only 1 out of 25 ways that they can both pick the man who is guilty. So the odds of 2 people closing their eyes and picking, accused, the odds of 2 people closing their eyes and picking the accused is 1 in 25. So is that reasonable doubt? If you're a jury, do you convict? Knowing that there's a 4% chance that maybe they just both got lucky and picked this guy, it seems overwhelmingly obvious that this man must be guilty if 2 people picked his voice, but there's actually a 4% chance that they just picked his voice at random. That means out of 100 trials, you're going to send 4 innocent people to prison, perhaps. Tough to think about, isn't it? But anyways, this is a fundamental counting principle in action. 1 out of 25 times, they could have made the same selection just by random chance.